The topic of our discussion today is Norton's theorem. So, basically whenever you encounter a difficult circuit, or rather a complex circuitry consisting of n number of sources, maybe dependent, independent, any kind of sources, and numerous points where energy is being dissipated, or in other way loads, in those cases it is very difficult to judge the circuitry. For example, if I ask you to calculate what amount of voltage is being generated in a particular point of a circuit of a computer motherboard, then that is a very tedious task. Why? Because basically it consists of numerous numbers of resistances, inductances, capacitances, and also sources. So, in those cases and in other real life cases, for example, when there is a transmission line or when there is a distributed network and you have to calculate the various parameters of the circuit, for example, power, current, voltage, etc., you will face very much difficulty while doing so. Now, in the previous class we have seen how Thevenin's theorem is going to help you out in those cases. Now, in this method Norton's theorem, it actually does the same thing, but in a slightly different way. As you can remember, in the previous class regarding Thevenin's theorem, any complex network was being converted to a much more simpler circuitry consisting of a voltage source and two resistances. One is the load resistance and the other one representing the total internal resistance of the circuitry, that is nothing but the representation of the internal characteristic of the circuit, and which only depends on the arrangement and values of the parameters of the circuit. Now, in today's topic that is the Norton's theorem, this theorem actually does the same thing, but the result after applying this theorem is a bit different from the previous one. So, let us before going deeper into the details, let us first briefly understand what is this theorem. So, this theorem basically states any linear active and bilateral network can be converted, however complex it may be, can be converted to a much simple circuit consisting only 3 elements. Just see the similarity between Norton's and Thevenin's, this is very important. So, any complex network can be converted to a much simpler network consisting 3 elements. One is a current source, that is called the short circuit current source or ISC. The other one is the load resistance. I think from the previous class you already know what a load resistance is, but we will discuss that in this class also. And the third one is called the total internal resistance of the circuit, that is Rin. And in this case also, this Rin represents nothing but the characteristic of the circuit itself. Why? Because this Rin, while doing this discussion you will come to know, this Rin is nothing but the total internal resistance of the circuit. That means it can only be changed if the value or the arrangement or both of the circuit's resistances are changed. So, this Rin is nothing but it represents the characteristic of the circuit itself. Now, what is the fundamental difference between a Thevenin's theorem and a Norton's theorem? In case of a Thevenin's theorem, the whole thing was converted, any complex circuit was being converted to a much simpler circuitry consisting of 3 elements, again a voltage source and 2 resistances, and the alignment or the arrangement was kind of in series. Every element of that case was in series. But if you look into the circuit, the basic difference of this circuit compared to that circuit is nothing but all the elements in this circuit are in parallel, as you can see in this. Now, basically both of these circuits are doing the same thing. Now, what are the differences, or why do we apply this theorem? We are going to come to that thing while this discussion is going to be continued.